We are in Rosen, Discrete Mathematics and its Application, section 4.1. We are talking about Theorem 4, which states that if you have integers a and b that are congruent modulo m, that is if and only if they're integers k such that a is equal to b times k, b plus k times m. All right, we'll use the definitions to prove this. So if A is, we'll assume the first claim, A is congruent to B mod M, then by definition of congruence, M divides A minus B. And then by the definition of divides, A minus B is equal to K times M. And then if we add B to both sides, we get A equals B plus KM. And then going the other direction, if we assume that A is equal to B plus KM, then KM is equal to A minus B, M divides A minus B, and therefore A is congruent to B mod M. All right. Theorem 5. If I have A is congruent to B mod M and C is congruent to D mod M, then I can add both sides of these congruences. Similar to A equal B and C equal D implies A plus C equals B plus D. We can do the same thing with congruences. A plus C is equal to B plus D mod M when A and B are congruent mod M and C and D are congruent mod M. And the same thing will be true for products, just like it would be for an equation. AC would be equal to BD. Okay. And here's our proof. If A is congruent to B mod M, C is congruent to D mod M. By our previous theorem, B is equal to A plus S times M, C is equal to D is equal to C plus T times M. We'll add them together and we'll combine terms that include M as a factor. So we get B plus D is equal to A plus C times an integer divisible by M. And B times D is equal to AC times an integer that is divisible by M. And if I subtract A plus C from both sides, or A times C from both sides, in that case, we demonstrate that they are congruent with the left-hand sides. So if 7 is congruent to 2 mod 5 and 11 is congruent to 1 mod 5, then 7 plus 11 is congruent to 2 plus 1 mod 5, and 7 times 11 is congruent to 2 times 1 mod 5. This next theory, well, this basically allows us to do algebraic manipulation of congruences, just like we do with equations. I can multiply both sides of a congruence by an integer. I can add an integer to both sides of a congruence. But in general, I cannot always divide both sides of a congruence by an integer, even if the sides are divisible by it. For instance, 14 is congruent to 8 mod 6 because 14 minus 8 is divisible by 6. But if I divide both of those sides by 2, I get 7 and 4, but 7 and 4 are not congruent mod 6. There are times when you can do that, and we will talk about the conditions for that later. This is a very important theorem for computing the modulus of very complex expressions. And here's a corollary to that. The proof of this is in the text. But what it says is that if I have A plus B mod M, then I can take the modulus of A, and if I want to, also the modulus of B, and I will maintain the overall value of the expression. And the same thing's true with multiplication. A times B mod M is equal to A mod M, if I like, times B mod M, as long as I'm taking mod M at the end. And what this means in general is that we can always apply the mod m function to any factor or term inside the argument of a mod m function and preserve the result. So if I have a plus b mod m and that's very complicated, a mod m is a smaller number and b mod m is a smaller number than b and maybe easier to calculate the end result.